So we're about to dive into a problem that is so ridiculously massive, trying to solve it with just raw power would literally break the laws of physics. It's a story that really proves that the most powerful tool isn't always a bigger machine, it's a smarter idea.
All right, let's start with a question that seems simple, but is actually kind of mind-bending. Could you build a perfect digital twin of this tiny little crystal? A 1 cubic centimeter piece of amethyst. And I don't just mean what it looks like. I mean simulating every single atom, every quark, every gluon, right from the ground up. Because inside that one little cube, you'll find roughly this many atoms. That is 700 septillion. To give you some perspective, that's more atoms than all the grains of sand on every single beach on Earth combined. So where would you even start trying to calculate how they all interact?
And that brings us to the first part of our story, grappling with what feels like a fundamentally impossible simulation.
So your first thought is probably the same one I had. Hey, we've got supercomputers for this kind of thing, right? Let's just point the biggest, most powerful machines on the entire planet at this problem and just let them run. But this is where we just slam right into what you could call the supercomputer wall. Turns out even our most powerful hardware hits a limit, and it hits it hard.
So, meet the current heavyweights, Frontier, El Capitan, and Fugaku. These things are exascale machines. That means they can perform over a quintillion calculations per second. That's a billion billion. Put it this way, if every single person on Earth did 1 calculation per second, it would take all of us over 4 years to do what these machines do in a single second. This is the absolute peak of our computing power.
And here's the reality check. Our very best machine tops out at around 2.8 exaflops. To simulate our tiny crystal for just 1 second, we would need a billion trillion exaflops. We're not just a little short on power here, we are orders and orders of magnitude away. We need more computers than we could ever hope to build.
But here's the real twist. Even if we had all the computers in the universe, it wouldn't make a difference. The problem isn't just about processing power. It's much deeper than that. It actually runs up against the fundamental laws of the universe.
Right, this is where things get really fascinating. We've moved beyond an engineering problem and into the world of fundamental physical limits.
Okay, so this brings us to this wild concept from physics called the Bekenstein bound. What you see here is the definition. Basically, it says there's a hard limit on the amount of information you can cram into any given volume of space before it just collapses into a black hole. Think of it like a cosmic zip file limit. There's only so much you can compress into a space.
And this is what really illustrates the true insane scale of our problem. The sheer amount of data you would need to perfectly describe the quantum state of every particle in our amethyst crystal is actually greater than the Bekenstein bound for that same cubic centimeter. In other words, the instruction manual is physically larger than the thing you're trying to build. The problem isn't just hard, it's fundamentally impossible.
So, is that it? The end of the road? An impossible problem with no solution? Well, not quite. Because it turns out we were asking the wrong question the whole time. We just needed to ask a smarter one.
And this was a question that changed everything. Forget more power. Forget bigger machines. What if the answer wasn't in the hardware at all? What if it was in the software, in a smarter algorithm?
And that brings us to the real solution, the algorithmic toolkit. These are the secret weapons that computational scientists use to tackle these seemingly impossible problems, not with brute force, but with intelligence.
So the core strategy here is something called multiscale modeling, and it's brilliant. Think of it like this. If you were making a map of a city, you wouldn't map every single brick on every building, right? You'd use super high detail for important landmarks and then broader strokes for, say, residential blocks. Well, scientists do the same thing. As you can see, they use those super expensive quantum simulations only for the most critical areas, like a tiny defect in the crystal. Then they zoom out and use faster classical models for bigger groups of atoms. And then for the vast majority of the crystal, they zoom out even further and treat it as one continuous material. It's all about applying the right level of detail only where it actually matters.
And multiscale modeling is just one tool in the box. I mean, look at this. There's a whole suite of these algorithmic superpowers. You've got machine learning, which can be trained to predict quantum interactions at a fraction of the cost. It's like a student who knows the material so well they don't need the textbook for every little problem. Then you have other things like the fast multiple method, which are just clever mathematical tricks to slash the number of calculations you need to do. Every single one of these is like a massive efficiency cheat code.
So how much of a cheat code are we talking about? Well, using just one technique, like a machine learning potential, can cut the computational cost by a factor of up to 1,000,000. That's not a 10% improvement, that's a complete and total game changer.
Which brings us to our final takeaway, really. This whole journey has been a classic battle, brute force power versus elegant intelligence.
You know, this quote here on the slide just captures the whole theme perfectly. For all the attention we give to faster chips and bigger machines, it's the smarter algorithms that have given us just as much of a boost in what we can achieve. The software has absolutely kept pace with the hardware.
At the end of the day, when faced with an impossible problem, the solution wasn't to try and build an impossibly big hammer. It was to step back, rethink the whole approach, and invent a whole new, much more intelligent set of tools.
And that's really the question to leave you with. This isn't just about simulating crystals, right? This applies to everything from drug discovery to climate modeling and material science. It really makes you wonder, what other challenges out there that seem impossible today are just waiting for the right algorithm, the right shift in thinking to suddenly become solvable?